Okay, we have covered some basics of HMI development and now roughly understand how everything works. But now when we have to start shaping up our HMI application, if I were you, I would start asking questions. How do you present technological equipment on a screen? How do you show different states of that equipment? Which colors do you use? What are the best practices? And when it comes to these design decisions in the industrial HMI world, there are usually two opinions. Come on, it's 2025. We don't have to reinvent UI design from scratch. Companies like Google, Apple, or Microsoft have entire departments who have been working on user interfaces for decades.
Yeah, decades.
Operators deserve interfaces that don't look like Soviet-era control panels. And nothing says industrial design more than neon gradients and fancy blinking animations. Standard exists so people can actually see critical information instead of getting blinded by someone's designer of the year ambitions. Sorry for wanting the HMI to look modern instead of designed on Windows 95. And I'm sorry you think an operator in a noisy plant wants an HMI to look like a smartphone trying too hard to be cool. Operators deserve nice-looking screens. They deserve readable screens. And colorful is readable, not when everything looks like a candy store explosion. Gray is boring. Gray keeps people from pushing their own buttons. Oh, those two. If you have been around industrial automation for a while, that would look familiar to you. Of course, those two viewpoints are the extremes of the whole spectrum of opinions. But the point still stands. Some developers gravitate more toward IT world best practices, and some insist on using industrial OT standards. Okay, Yuri, it was a nice little play and everything, but what's your point of view? In the end, we're just the audience. You're the one forcing us to watch whatever you decide to show. Fair point. Personally, while I think both sides have valid arguments, I lean more toward the OT approach. But that doesn't mean I ignore the good ideas coming from the IT world. For example, if during a breakdown you can highlight the exact faulty component on a 3D model with a red highlight, maintenance team will praise many times that clever HMI designer. At the same time, you don't need to draw a pipeline 10 pixels thick with gradients, shadows, and full Hollywood production budget. A simple schematic style line does the job perfectly. Now, what are the OT HMI standards I was talking about? Surprisingly, for such an important area of automation, the field isn't all that heavily regulated. One of the few established guidelines is the ISA 101 Human-Machine Interfaces Standard. It covers things like menu hierarchies, screen navigation, graphics and colors usage, dynamic elements, alarms, you name it. At its core, ISA 101 promotes the idea of a muted, almost colorless interface during normal operation. Then, when something goes wrong, the issue immediately jumps out at the operator. The standard focuses heavily on a situational awareness, which simply means the operator can look at the screen and answer one question immediately. Is the process or the machine healthy? Another great source of practical guidance is the High Performance HMI Handbook. It's built on the same ISA 101 principles, written by many of the same authors, and conveys the same ideas, just in more accessible, example-driven way. These resources aren't free, but if you or your company are serious about building solid HMIs, investing in either the book or the standard is absolutely worth it. Nevertheless, there are many free resources dedicated to high-performance HMI topics, like webinars, guidelines, best practice documents, etc. I'll leave some of the useful links in the description below the video. Viewers familiar with ISA 101 and high-performance HMI principles might argue that this standard is focused primarily on process industries and large HMI systems such as SCADA or DCS. And they would be right. There is a difference between 32-inch 4K resolution SCADA screen and 7-inch panel that we have here. But first, the majority of concepts and principles could easily be transferred to machine HMI, and second, there's simply no major industry-wide standard for HMI in machine automation field, so we'll use what we got. However, the fact that there is no universal standard doesn't mean there are no great machine HMI examples. And if you think about it, what could be a better showcase of thoughtful, ergonomic, high-performance interface design than the glass cockpit of modern airliner? Seriously, pause the video and try to name a machine that carries more responsibility, must operate flawlessly, and yet still this common. Go ahead, I'll read your comments below the video, maybe I'm missing something. Have a look with me at the Airbus A320's HMI. Notice how minimalistic it is. Static elements are plain white, dynamic values are green, units have their own consistent color, and anything abnormal pops up in orange. Analog indicators are as simple as you can possibly design it. Even the aircraft itself is just a clean outline, no gradients, no shadows, no flashy animations. And if anyone in the world has the budget to make their HMI look like a sci-fi movie, it's Airbus and Boeing, yet they stick to simple, efficient design. That should tell us something. Well, I hope this little theoretical detour was useful, but enough talking. We need to get back into Panel Builder and actually design something. Let's start by cleaning up the first page and the navigation template. Now we need to depict somehow key equipment, like pumps and a valve on the screen. How do we do that? Well, there are standardized representation of key technological equipment, which you can find in standards like ISO 14617, graphical symbols for diagrams, or ISO 10628, diagrams for the chemical and petrochemical industry, or ISO 7000, graphical symbols for use on equipment. Regardless of standard you choose, common components like pump would be the same. Circle with an angled line inside, indicating the direction the fluid is being pumped. We could use the standard shapes from the widget library, but I prefer a different approach. Let me show you. In the same widget gallery, under Images, you'll find the Multistate image widget. As the name suggests, it needs an image to work with. You can download symbols from the standards I mentioned earlier, or you can simply create your own. And I would highly recommend getting comfortable with any vector-based graphics editor. It will be incredibly useful in your human-machine interface projects. I'm using free and open source Inkscape editor, which works natively with SVG files. Which in turn are supported by Panel Builder. Let's start by drawing a perfect circle. Hold Shift while dragging. Then, with snapping enabled, draw two straight lines, one from the top to the left and one from the top to the right. Set the stroke width to 2 mm. You'll need to experiment a bit to find the line thickness that looks best for your panel and image size. I did those experiments beforehand, so we don't waste any time. Now, about colors. Some people will say just pick something and move on, but this gentleman here would strongly disagree. His name is Johannes Itten, a Swiss painter, designer, teacher, and arguably one of the most influential figures in modern color theory. Yes, color theory is a real discipline. It studies how colors interact, how they influence perception, and how to achieve specific goals by combining them intentionally. You don't need to dive into the entire theory, but you should choose your colors consciously. Use color palette generators to find combinations that actually work. Check contrast and readability between foreground and background. And always test your color choices to see how they appear to people with different types of color blindness. Copy the stroke color from the palette and apply it to all the lines. For the running pump, I'll use a white background. Then crop the page to match the size of the circle and save the file with an appropriate name. After that, change the circle's background to a darker gray to represent a stopped pump. Back in Panel Builder, resize the widget to a square. Around 50 by 50 pixels works fine. Then open the Images property and import the two files we just created. Index 0 for the stopped pump, index 1 for the running pump. Now if you change the widget's value to 1, you'll see the pump graphics switch to the running state image. One thing I forgot earlier. We should also change the page background to a color from our palette. And while we are at it, since the palette is already defined, why not save it in custom colors? That way it's always available whenever we need to pick a color later. Let's add a label to show the pump's name, P1. Generally, all static elements, text labels, lines, image outlines should use the same color. In our case, that's dark gray. This helps the operator consciously ignore anything that never changes and focus on the information that actually matters. Next, we can start drawing the lines that represent the pipes going to and from the pump. We've already chosen the color, and for the thickness 2 pixels looks pretty good to me. Now let's connect the Multistate image widget, the one representing the pump, to the actual tag. And here is where we hit a little problem. The pump can run either through a drive or through a direct online contactor. Both conditions mean running, but they come from different signals. Sure, we can create another variable in the PLC that combines the states and send that to the HMI. But I prefer the idea that anything only needed for the visualization should be handled inside HMI, not cluttering the PLC logic. So how do we combine those two signals on the HMI side? In the text selection window, you'll find a formula option. Basically, it works like a one-line function. Click Insert Formula, then Formula DB button to see all the built-in functions. Find OR and select it. Now you've got the function, but it's missing arguments. To add them, just pick the tags you want from the list, click them one by one, and they'll drop right into the formula. When the function is complete, hit Accept Formula so the software can validate it. After that, press OK, and your data link will now use the OR combination of two tags. The next step is to display the pump's operating mode, auto or manual. Fortunately, we already know how to do this using the message widget. Start by adjusting text strings. Then change the text color to dark blue from the palette. This will be our standard color for any dynamically updated values. Hide the widget's frame, adjust its size, and position it just below the pump image. Finally, link the widget's value to the appropriate tag so it updates automatically. Now it's time to set up the VSD DOL indicator. When the pump is running, we want to show how it's being controlled. The process is almost identical to creating the auto manual message. Actually, you can simply copy and paste that widget. Update the text strings to DOL and VSD accordingly, and link the widget's value field to the Run VSD Pump 1 tag. For the final touch, we'll make sure that indicator is hidden whenever the pump isn't running. Since it's neither in DOL nor VSD mode, at that point there's nothing to display. In the widget's general properties, find the visible field and attach it to or combination of the run.dol and run.vsd tags. Since we already started with VSD control, let's display the actual speed the pump is running at. Bring numerical widget to the canvas and change text color to blue. Make it bold. Change value to 100, the maximum speed in percentage. This way it's easier to see dimensions of the widget when its value maxed out. Maybe make it even bolder by changing font weight from light to medium and connect it to drive speed tag. Add the label widget. This will be your little percentage suffix. Make the text smaller and align it to the left. The speed value itself should be aligned to the right, so together they look like one clean unit. Use the muted gray color from the palette. It's not essential operational information, so there is no need to compete for operators' attention. Next, we need to hide the both numeric value and the percentage label when the VSD isn't running. You could set visibility for each widget individually, but it's more efficient to group them together and control the visibility of the entire group with the appropriate tag. Now we need to indicate when the pump is in a fault state. Here is my way to do it. Add a rectangle shape widget, remove the fill and set the stroke color to the red from our palette. Resize and position the rectangle so it frames the pump image and all its related dynamic values. For a clear visual cue, add an icon, a circle with an exclamation mark. You already know where to find these symbols and how to adjust them in a vector editor, so you're well equipped for this step. Place the icon in one corner of the rectangle, group everything together, and then link the group's visibility to the pump fault tag. Since the second pump is identical to the first, simply select the whole group, copy it and paste it. After that, it's just a housekeeping. Relink all dynamic elements to the corresponding tags for pump 2 and adjust labels. With both pumps in place, we can do the surrounding piping. And where a pipe leaves the screen or connects to another part of the process, it's helpful to indicate where it's going. A small label will save an operator from doing guesswork. Okay, it's valve time. I've already prepared the basic outline of the valve symbol, so we just need to produce its different visual states. First up, idle. Nothing is happening, so we give this symbol a neutral tone. Change the fill to our inactive gray from the palette and save that as the default image. Next is the opening state. We simply turn bottom half of the valve white, so it visually resembles an arrow pointed upward. Save that as a second file. Then we repeat the idea for the closing state. This time the upper half becomes white, hinting an arrow pointing downwards. Save that one as well. Go back to Panel Builder and drop in a Multistate image widget. Import the 3 valve images we just created and adjust the size and position so they sit nicely on the screen. Now, if you manually change the widget's value, you'll see it cycles through the states. 1 opening, 2 closing, 0 idle. Now comes the slightly tricky part. We only have 2 Boolean tags, valve opening and valve closing. But the widget needs a single integer value from 0 to 2. How the heck do we get from 2 booleans to 1 integer? You guessed it right, it's formula time. Find the open command tag and add it to the formula. Then add the close command tag and multiply that one by 2. Here is what's happening. If both tags are false, then the formula evaluates to 0. Panel Builder uses JavaScript under the hood, and JavaScript implicitly converts false to numeric 0. If only the open command is true, the left side becomes 1, the right side stays 0, and the result is 1. If only the close command is true, the left side is 0, the right sides become 2, and the result is 2. Both tags can't be true at the same time, at least they shouldn't, so you never hit 3. But if you want a little bonus exercise, try using the built-in min function to cap the result at 2, just in case both tags ever turn true simultaneously. Now we can finish up by adding the piping and labels around the valve. We're still missing one important piece of information: return and supply temperatures plus suction and discharge pressures. Let's start with the return water temperature. Copy an existing numeric value and move it somewhere near the From Consumers label. Now here's a neat trick when working with groups or complex widgets. You can double-click a group to enter it. Everything outside fades out and only the elements inside keep their real colors. That's your visual cue that you're editing inside the group. You'll also see a breadcrumbs path in the top left corner showing exactly where you are. While we're still inside the group, let's change how the temperature value is displayed. Add one decimal place, set a more realistic default value, resize the bounding box, update the unit label to degrees Celsius, and finally relink the numeric widget to the actual temperature tag. Remember those channel fault flags we created earlier when scaling the analog inputs in the controller? Let's use them here. Copy the red rectangle we used for the pump fault, resize it, and place it around the values so we can instantly see if the reading is trustworthy. Just make sure to relink the visibility property to the sensor fault tag. Repeat the same for supply water temperature, discharge, and suction pressure. Nice! It starts to look like something. We can also update the page title to match what we've just built. While we're at it, rename the page in the project tree as well. And the next page too. That one will be our feeding subsystem. Jump over there, change the title to feeding subsystem, and since it also has 2 pumps, let's save ourselves some time and copy them from the page we've already made. Now it's just a matter of rearranging the elements and deleting everything that doesn't belong to the feeding subsystem. We're still missing valve KV2, so let's switch to the vector editor and create the images. I started with parts of the control valve symbol and added a circle in the middle to indicate it's a shut-off valve. First, set the fill to the gray color from our palette and save it as an off-state image. Then change the fill to white for the open state image. Back in Panel Builder, the process is exactly the same as for the control valve and pumps. This is how it will look after all the setup and linking. Last thing, I promise. I just remembered we need to update the navigation menu. Go to the dialog page and change the labels for page 1 and page 2 so they match the new content. Now let's simulate and see how everything we've built behaves. Open the text simulation panel and filter it to show only the tags used on the current page. Less scrolling, less hunting for the right tag. Start with the auto manual modes. Great, that works. Start pump 1 directly. Check. Now through the drive. Perfect. Change the speed to say 83. As expected. Stop the pump and trigger a pump fault. Yes, that works too. Play around with the discharge pressure values and its fault. Perfect again. In the same way, you would go through all the elements and simulate their behavior online to make sure everything responds correctly. Oh, I almost forgot the valve. Set the closing tag and the arrow pointing down. Now the open tag works perfectly too. Let's take a look at the feeding subsystem. Yep, that's looking good. I know this chapter ended up being longer than usual, but I didn't want to split an important topic into parts. Thanks for sticking till the end, and I'll see you in the next one. Stay safe.